All right, what you'll see in front of you is the modulus of elasticity for birch wood. So what I talked about in class was that modulus of elasticity has to do with the strength of a beam based on the material. And so these numbers have already been all calculated, and you can go to Google, just like I did here, and figure out that number based on what material it is that you're using. So we're going to use the number that I found here, which is the 1,720. KSI, and we're going to put that into the equation that we did in class, and we're going to hope to get close to the same deflection that we did in the inventor module that I just ran. So I'm going to share my screen in hopes that we can work it out using the whiteboard feature. Okay, here we go. So we'll go ahead and make this full size, and I'll move this over. So we're going to run through an example calculation of the activity that we did in class, but we're going to do it with the inventor model. So some of this information that you will need to know, I'll give to you right now. The delta max that we are trying to get is going to be 1.6. All right, so that is, again, the difference from so that is the difference between the beam without a load on it, and then after while someone is putting a force on it, that displacement is going to be the deflection there. So 1.6 inches would be good if we could get close to that. The modulus of elasticity, which we just looked up on that table, was 1,720,000 psi. All right, other things that we need to do is we need to find the moment of inertia. We can do that together. The length of the beam is 8 feet. And I don't think there's anything else. So to find the moment of inertia, we need to do the equation. And this is, again, only for beams. Every shape has a different equation. So it's 1/12 base times height cubed. So if you looked at the beam we used, we kept it in plank form, and the bottom was 3.5 inches, and the height is 1.5 inches. It's supposed to be a 5. There we go. All right, so I'm just going to plug that into this equation up here. So we have 1/12 base, which is 3.5, times a height of 1.5 cubed. And we'll end up getting that to be 9.984. And that would be inches to the fourth if I would have carried my units. There we go. All right, so that's really all we need other than the equation to go about this. And so the equation is delta max, which is the displacement, equals F, which is force, which just realized we'll need that. So I'll give that to you in a second, times the length of the beam cubed over 48 times E times I. So the other important part that I forgot to tell you was the force load that we applied, if you remembered from the inventor model, but it was 150 pounds. Okay, so now our goal is to see if we can get this to be 1.6, because this is what was given to us in the simulation. So all I'm going to do is plug in numbers. All right, so I don't even have to manipulate the equation. Everything should be really straightforward. So the force is 150 pounds. All right, the length of the beam, so is 8 feet, but I need to change it to inches to keep my unit. So I'm going to multiply that by 12 in order to change it over to inches. And then, actually, I don't like how I'm going to get rid of that unit because that makes it, here we go. So we're going to take 8 times 12, so we're going to end up getting it to be in inches. All right, and then it's going to be over the 48 times E, and we're using the E we found on Google. So 1,720,000 pounds per square inch times then the moment of inertia, which is 0.984 inches to the fourth. All right, so these are really big numbers to be working with. So I'm going to take the top and I'm going to use my phone as my calculator. And I suggest you do the same thing just to make sure we all get the same numbers. So 150 times 8 times 12. Oh, cubed, very important part. See, my number wasn't huge, and then I forgot that I left that off. See the cubed here? I needed to make sure I put that there. So let's go back and revisit that. So 8 times 12 is 96 to the third. then times 150 gives me this really, really big number. Okay, over, and then let's go to the bottom. So I'm going to take 0.984 times 1720000 times 48, and I also get a really large number, 81,239,040. All right, so now I'm going to divide these two and see what I end up getting. All right, and my final answer is 1.63. So I would call that pretty accurate. We did a decent job. It's pretty close to the 1.6 that was given to us in the simulation. So that is it for this video. Hopefully, you found this to be helpful. Thank you.